Okay, we're going to start linear regression notes and talk about correlation today. So let's define what a scatter plot is. A scatter plot shows the relationship between two quantitative variables measured on the same individuals. Okay? So this is when we have what we call bivariate data. So how do we examine a scatter plot? We need to first look at the overall pattern and for any striking departures from that pattern. So we can use a sentence to describe the overall pattern by stating the direction, is it positive, negative, by stating the form, and we're gonna only deal with linear or nonlinear in AP stats, and the strength, is it weak, moderate, or strong? And we need to know any important departures, so any possible outliers. So here we have a scatter plot of a body weight in pounds versus pack weight, how much weight they are carrying in pounds. So if we are going to describe this scatter plot, we could say that, well, yes, I could draw a line going in between those data points where about half are above, half are below. Okay, so there is a moderately strong, the points are pretty close to the line, not too far apart, but not exactly on the line, so moderately strong. It's positive. If we were to find the equation of that line, it would be a positive slope, and it is linear. It does create a linear pattern. So there is a moderately strong, positive linear relationship between our X body weight and Y our pack weight. We can also make the general statement, it appears that lighter students are carrying lighter backpacks, okay, which seems reasonable. We can also notice that we do have one possible outlier out here. The hiker with a body weight of 187 pounds seems to be carrying relatively less weight than the other group members. So suppose we have a new set of data set and we found the age and weight of a sample of 10 adults. So I listed the steps in the calculator of how to create a scatter plot. So let me show you how to create a scatter plot on the calculator of this age and weight.
I need your consent on a few items to continue.
Okay, so we have our graphic calculator here. To input data, you're going to go to your list and spreadsheet, so this Excel looking button. And first thing you need to do is we need to label our columns. You can use X or Y. If it populates other numbers, that means that there's another tab here that's already called an X or Y. I'm going to use what our actual words are. So we have age and we have weight. So first step, label your columns. Then we're going to input our data values. So we have what, 24, 30, 41, 28, 50, 46, 49, 35, 20, 39. And we have 256, 124, 320, 185, 158, 129, 103, 196, 110, and 130. Again, always double check to make sure that you got all your data points. We had 10 adults and I do end at cell 10. So make sure one of the box numbers is highlighted. Then you're gonna hit menu. You're gonna hit data. And then you're gonna click quick graph. If you do not have access to quick graph, it is because you did not highlight one of your data points, okay? But if it's highlighted, click quick graph. And notice we have a graph here, but it doesn't quite look like a scatter plot yet. That's because we need to label our axes. So what do I have on the x-axis? I'm going to click on weight. I don't want weight on my x, I want age. And on my y-axis, click it, I want weight. So here gives us a nice pretty scatter plot of our age and weight. Well, let's look at the question. It says, is there a relationship? Is there a relationship between age and weight? Is there a relationship between age and weight? Well, if I look at the scatter plot, there's not much. Maybe you could say a weak relationship. If I put a line going halfway above, half below, the points really aren't close to that line. Okay, so while we could say not really, or we could say very weak, and notice since the ages of are all adults, let's think about that. People as adults don't grow much taller. I mean, yes, we may grow wider in certain ways, but because we're only dealing with ages from 20 to 50, we're not going to see much growth, at least tall-wise, between that time period. So let's change this data set, and instead of answering the question, is there a relationship between age and weight? Is there a relationship between height and weight? Is there a relationship between height and weight? Let's go back to our scatter plot. Okay, and now I'm going to, I can just write over my data values. Instead of age, we're gonna change this to height. Now I'm gonna enter my new data value. So I have a height of 74, 65, 77, 72, 68. Notice the weights are all the same. So on my scatter plot, I now have a new variable. My x-axis is now height. And again, y-axis is still weight. Make sure it's still weight. And now let's look at my scatter plot. Is there a relationship between height and weight of these 20 adults? And what do we notice? Definitely, if we were to draw a line between the middle of those data points, we definitely have a positive, linear relationship. Okay, so height is better correlated to weight as opposed to age. So yes, we definitely see as height increases, weight increases. And is it positive or negative? From our linear equation line, it would definitely be positive, and it is definitely strong. So the closer the points in a scatter plot are to a straight line, the stronger the relationship. The further away from a straight line, the weaker the relationship. So let's identify these scenarios. Are they a positive association, a negative association, or no association? We have the heights of mothers and heights of their adult daughters. Well, let's determine the height of a mother and their height of their adult daughters. Well, that probably has a positive relationship. Taller people tend to have taller children, not all the time, but if you were to pull 100, that would probably be most the case. That's also true just based on nationality. Certain nationalities are taller than other nationalities. What about the age of a car in years and its current value? So as a car gets older, are we staying the same? Are we increasing? Are we decreasing? You're probably going to be decreasing the cost of that car. And those of y'all getting ready to drive soon, the minute you drive that car off the lot, it's lost value. Of course, there's always exceptions to the rule. If you have a classic car, those increase. But again, that is not a norm. That will be a very small number out of your population. What about the weight of a person and calories consumed? So how much somebody weighs, how many calories they eat, well, that's going to be positive for the most part, right? Okay, the more you eat, the more weight you're probably going to gain. Of course, there's always outliers, people that can eat what they want and not gain. Eventually, it all catches up to you. What about the height of a person and the person's birth month? So does the month a person is born, does that affect the height of a person? Well, no, that is no association. And even if you had the data for that, you can't say that the month that they're born is causing a person's height. Okay, it might just happen by chance, but one doesn't cause the other. So what about the number of hours spent in safety training and the number of accidents that occur? That would probably be a negative association as well. So as we spend more hours in safety training, hopefully, if we get more educated in safety, the less accidents are hopefully occurring, which is exactly why the government requires you to take safety classes if you actually do get a ticket or in an accident, as there have been statistics that prove that. So how do we know for sure if there is a relationship between two variables? We can find what's called the correlation coefficient. That is the R value. So correlation coefficient is a quantitative, it's a number assessment of the strength direction of the linear relationship between two bivariate quantitative data. Okay. So R value only deals with the linear relationship. It's only fitting the points to a line, no other type of equation. It could also be used a parameter called rho, fancy P. You won't see this too often, but be aware that it relates to R. And the statistic, again, it is a number value with no units. And yay, this is how you calculate it, but you don't ever have to calculate it by hand. It is on your AP Stat formula sheet. Okay. Again, you just need to know what the variables represent. 1 divided by, this is sample size, minus 1. This big means sum everything up. So we're going to take the data point minus the mean divided by standard deviation of the X. We're going to take the Y coordinate point minus the average of all the Y's divided by the standard deviation of all the Y's. So because we have bivariate 2 columns, okay, you have a standard deviation for X, you have a standard deviation for Y, but calculator is going to do the work for us. Just be aware and be able to find it on your formula sheet. So properties of R. How do we define R? It is a number between -1 and 1. Okay, if every single data point is smack dab in a line, we would have an R value of exactly 1. Again, if every point is smack dab on the line and it's going negatively, we would have an R value of -1. Cannot have an R value above 1 or below -1. Okay, that would be like having more than 100% of the points on the line. If an R value is 0, that means there is absolutely no correlation whatsoever. Again, it's very hard to get an exact correlation of 0. Most of the time it will be a number close to 0, not exact. We can describe a R value as weak if it's between 0 to 0.5 would be a weak positive. 0 to -0.5 would be a weak negative. We can describe a moderate positive as 0.5 to 0.8, a negative moderate as -0.5 to -0.8. And we can describe a strong positive as 0.8 to 1, or a negative strong correlation as -0.8 to -1. Okay, so cutoff 0 to 0.5, weak, 0.5 to 0.8, moderate, 0.8. Above is strong. Nothing above 1, nothing below -1. So here it shows you some visuals of what scatterplots might look like at different correlations. Notice when R equals 0, it's just kind of random. You know, if I try to draw a line between here, you know, half the points are very spread out from the line and not really much pattern. Notice on the second one as R equals -0.3. Notice where most of the data points is, I can draw a line negatively down. But again, the points aren't very close to it, okay? Hence why it is weak. Notice if our R is 0.5, we're getting moderate. Again, you could call this moderately weak. If you're unsure, combine the two. Never hurts to add in an adjective. Points are getting closer in a line and it's going in the positive direction. Notice negative 0.7, I can draw a line down negatively. And points are getting closer and closer. By the time we get to 0.9, oh, they're getting really close to a straight line. And an R value of negative 0.99 is almost an exact line. Okay. Real world data, you're going to rarely find an R value of exactly +1 or exactly -1, but doesn't mean it can't happen. But most often with real world data, it's probably not going to be a perfect line. So let's practice finding the R value, because again, we don't want to calculate all that by hand. Let's let the calculator do the work for us. So here we have data that is speed limit and average number of accidents. Speed limit and average number of accidents. So let's pull back up that graphing calculator. So let's go back to the beginning, go back to your list and spreadsheets. And here I have a speed limit, right? So I'm going to label it miles per hour. My second column, I'm going to label accidents, ACC. Again, you must label your column. It will not graph or do any calculations without the columns labeled. And then let's input our data. So we have 55, 50, 45, 40, 30, 20. Then we have 28 accidents, 25, 21, 17, 11, uh-oh. Ended at the wrong one. So I've got 28, 25, 21, 17, 11, and 6. And again, always count. I have 6 data points. I ended at cell 6. I am good. Again, the steps are listed here for how to find it on the calculator. Okay, so first it says we're going to calculate the R value. We're going to calculate the R value. So how we calculate the R value is we're going to use, make sure that one of your data points is highlighted. We're going to go to menu. You're going to go to statistics, stat calculations. And we want the third one, we want a linear regression. Always choose MX plus B. Think back to your algebra classes. So menu, statistics, stat calculations, and we are calculating the linear regression, MX plus B. It asks for our X list. Well, what's our X list? Our X list is miles per hour. Our Y list is accidents. And just click enter, don't need to change anything else. And notice here, we're going to talk about in a later chapter how we actually get this linear regression line. It will tell us our slope, our y-intercept. But today we're just going to want to know about the R value. So the calculator will actually do the complicated calculations and tell us the R value here, which is 0.99. Well, if I have an R value of 0.99, oh, that's pretty darn close to 1. And if we want to visualize the data, this would be a strong positive, right? If we want to visualize the data, click on a data point. We can quickly pop up the graph. So do data, do quick graph. And again, X, I want miles per hour. My Y-axis, I'm doing accidents. And notice that's almost a perfect straight line, which is why our R value is as high as it is. So again, our question was calculate R. R is 0.99. 0.996 if you want to. Do not round it up to 1 unless it is exactly 1. And how do we interpret it in context? Interpret means we need a sentence relating it to what in the world we're talking about, okay? So there is a strong because it's greater than 0.8. Positive because it's positive, always a linear relationship with AP between what two variables, speed limit and average number of accidents per week. Okay, so if it says interpret, that means I need a sentence describing what these numbers represent. So the value of R does not depend on the unit of measurement for either variable, okay? So if I have a listed data set and I find R, and you can do this on your calculator for time purposes, I will tell you. If we find the R value, we'll find the R value to be 0.918. Now, what if I were to change, X is currently in millimeters, well, what if I were to change it all to centimeters and find R? Well, if I'm going to change it to centimeters, that just means I'm changing all of my X, right, with the same Y. If you find R, it's still going to be the same, okay? As long as your units are exactly the same, change for each data point, it's not going to affect your R values, okay? So it does not depend on the unit. Notice we don't have any units with the R value, okay? Unit, R does not include units. Because the value of R also does not depend on which of the two variables is labeled X, okay? If I were to actually calculate the R value here, notice I'd still get R value of 0.918, okay? And this was when I swapped X and Y. So it does not matter, you'll get the same R value. R value has no units, and it does not matter if you switch X and Y. They would still be correlated the same. As X increases, Y increases is the same as saying as X decreases, Y is decreasing. The value of R is also what we call non-resistant. Okay, non-resistant means it doesn't stay the same. It doesn't stay the same, it means it changes, okay? So if we have this data set here, we have X and Y, and for your purposes, I already graphed it here on the left. Or actually, graphed on the left is the previous ones that we had. Notice in this previous example, we had a value of 2412, right? So that is a scatter plot on the left. This is with 2412. Now what happens when I change this 12 to a 22? Well, let's look at my scatter plot. Well, if I'm changing 12 to 24 to 22, I now have an outlier, right? Well, this guy definitely is going to affect this line, right? Well, here I had a point on the line. Well, if this guy's up here and the line is here, that means that my points are not as close to the line. So if we were to actually run and find the correlation coefficient, I'd only get an R value of 0.627. Okay, so they are what we call non-resistant. They don't stay the same. Outliers affect the correlation coefficient. Or even possible outliers affect the correlation coefficient. The value of R is a measure to the extent to which X and Y are linearly related. So we're only saying how well it fits a line. Value of R close to 0 does not rule out any strong relationship between X and Y. It just means it's not a linear relationship. So if I have a set of data points that makes this graph, well, I could definitely see a shape, right? But when I find the R value here, the R value, if I were to do a least squares regression line, would probably be pretty close to 0. That's not making a line. Okay, but it doesn't mean that there's not a relationship. It just means it's not linear. This one actually makes a quadratic, which would mean that we should have made a quadratic regression. And we did a little bit of that in Algebra 2. So let's look at some real world example here. Here we have some real data on a famous example of a correlation study. And we have different years. And we have for each year, the number of Methodist ministers in New England at the time. And we have the barrels of rum that are imported to Boston for each year. So you can graph this on your calculator if you want, and due to time purposes, I will just state if we actually graph it, we do our menu, statistics, stat calculations, least squares regression line, and find the R value. We're gonna get an R value of 0.999. Well, wow, what does that mean? Do we really think having more ministers is going to increase our barrels of rum? No, okay, just because I have a strong correlation does not mean that, oh, if I add more ministers, that means that's gonna cause more rum consumption. Just because something is correlated does not mean that it causes it, okay? If you think about what's happening in New England, you had the whole prohibition ended finally around the 1930s, which might add to the increase in rum. And before that, when you had prohibition, the US wasn't making any alcohol. So of course they had to import it. Okay, so there's lots of different things that can affect this. It does not mean that, okay, it is the increase in ministers that is actually causing the increase in rum. Okay, so key point here is just because something has a strong correlation, correlation does not imply causation. And we cannot say it enough. Correlation does not imply causation. Okay, we can say something is correlated, but that doesn't mean that one causes the other. That concludes our notes on correlation.